Okay. Um, I hope you can read these questions. It's still the say the related rates. Okay. So last time we are discussing the related rates. So you will have some problems. Okay. You have some cases. Um, it will relate with the rate of change. Okay. So there will be several objects or maybe person or anything that can move. Okay. And then you need to relate one object to other objects in terms of rate of change. Okay. So in here, okay, you see that two sides of triangle. So you have two lines that will make up a triangle, but the angle itself can be changed. Okay, the angle can be changed. The length is fixed, 5 and 8 meters in length. Okay, so the angle is increasing. Okay, so it has the rate of change of the angle. So this is the theta, d theta over dt. Okay, this one. Okay, so the question is asking find the rate at which the area of triangle is increasing. So as the theta increasing, the area also increasing. So it's asking what is the rate of change of the area. So you have an area of triangle that increasing, and that is what you need to look for. Okay. And it's asking when the fixed length is pi over 3 radian. And the triangle is it's not necessarily the right triangle, meaning it's not the 90-degree, not 90-degree triangle. So you need to find formula for the triangle. So it has length 5 and 8. I just make this is maybe 5, this is 8, and it has a theta. And the theta, we know that from the information, we know the rate of change of the angle is 0.06. Okay, so I have this as my triangle. This is theta. This is 8. Yeah, 8, 5 should be shorter, but yeah. Or let me write this as, let me generate the general rule for triangle. So let me write this is A, this is B. Okay. If it is the right triangle like that, it's 90-degree. If this is A, B, the area should be of AB, right? But this is not a right triangle, okay? So you need to make some cross cut here, making this 90-degree, and this is the height, okay? It's still the uh, half the h, okay? But the h is we can develop from the sine. Sine theta is h over a, so h is a sine theta. Okay, so you can have your area half. Let me write this a b sine theta. Okay. So every time you got the the general rule, like this one, the area, what you need to do is just derive this area. Okay, derive with the d dt. Okay, so a just derive with the t with time. Okay, so we'll get the directly dA over dt, and then derive all. Uh, this is 5, 8. Let me multiply all of this and become 40 and divide by 2, it's 20. So 20 sine theta derive, it's become the 20 cos theta d theta dt. This d theta dt we get from the information. It's 0.06. Okay, this 0.06, and we can use this 0.06, and we get the uh, dA dt is 20 cos when theta is pi over 3. So this is pi over 3. So it's half, right? Half, and then 10, 6. It should be 0.6 meters square per second. Okay, it's still simple related rates problem. Okay, so you have the cases, you have the event, okay, and then you need to connect uh, all the objects with some uh, related rates formula. Okay, um, it can be Pythagorean, area of triangle, circle, geometry, and all the usually the formula will be not too complicated. And then after you found the formula, you derive the formula, okay? And you need to find uh, whichever the questions is asking. Okay, maybe one more example, and then I can move to another section. Or maybe later, if we find any difficulty in related rates, we can go back to some examples. Okay, so let me go back. I think this already done yesterday. And how about this? Let me erase this picture first. Okay, so you have a conditions of two car. Okay, uh, you have A and B. Uh, that's mean miles per hour. So 50 miles per hour, 60 miles per hour. Okay, so car A and car B is traveling. Car A is traveling to the west. Car B to the north. They both uh, go for the intersections. Okay. And then the question is asking at what rate are the car approaching each other? It doesn't say it will meet, but it will approach each other. Maybe one will go away and the other will go here. We don't know because we haven't yet calculate. So the question is asking at what rate the car approaching each other when, okay, the car A 0.3 miles and B 0.4 miles from the intersections. Okay, so you have intersections, and from this point of intersections, 0.3 and 0.4 towards it's the A and B. So when the car A and car B at that point, okay, what is the rate of change? Okay, it's not asking necessarily the rate of change in A or in B, but both. Okay, so you need to have another object to view these two cars. Okay. Do you get it? If you in a car, you see another car, you yourself has a rate of change, right? You move, right? And the other also move. Can you know the rate of change of the other? You need to have another measurement, right? Because you are moving. You cannot really sure the rate of change of the others because you also move, right? It's relativity, right? So you need to have another fixed point that also can be used. Okay. So let me draw the intersection. Okay. And let me draw the car. This is A. Oh wait, this is B. This is B. This is A. Right? Yeah. This goes for 50 miles per hour. This is go for 60 miles per hour. So the question is asking when A is 0.3, maybe I will make it here, this 0.3, and A is at 0.4. What is the rate of change? So again, because all of the related rates questions, problems, case, they are having at least one formula, at least one formula. You need to think what formula that can be described from this picture. Okay. So before I already show you, and last week, the area, like the circle, can be bigger and bigger, or maybe the triangle before can be bigger and bigger. And here, what formula that you can think of from this picture? I think the number is already obvious, right? 3, 4. What's the other? 3, 4, 5, right? It's already Pythagorean. So you have some line here. That's when A is changing, B is changing. If imagine the line is, for example, the first one is here, the initial point. When B moving and A moving, the line also moving, right? So we can make that line as our point of view. So we can compute that rate of change of this line in terms of all these two cars approaching each other. So when these two approach each other, this line also moving. So let's just use the Pythagorean formula to write down all the relations here. Okay. Let me move this to another page. So let me draw the first line is here, and then it goes here. So let me, if this is A, B, let me write this C. Okay. So A squared plus B squared is C squared. Okay, that's the formula that we can relate from this picture. Okay. Let's just derive this formula. Okay. So whenever you find at least one formula, and you are sure that this is the formula, just derive. Okay, derive through ddt. Okay, and see the form. Okay, 2a dA dt plus 2b dB dt is equal to C dC dt. Okay, let me write the dA dt as in the example, is the in the information. So A is traveling 50 miles per hour. Okay, but here this is also one key important. Okay, because I make ABC as length. Okay, it's length fixed. Okay, when A and B move, the length is shorter, right? The length is shorter. Uh, so in my case here, I want to make this as -50 because it's getting shorter. Because I make this as length. Okay. Positive and negative in if you write in exam, it doesn't really matter as long as you have consistency. Okay. If you want to say this is positive, that's okay as your average speed. That's fine. But I want to make it negative because I see the triangle as fixed length and then reduce shorter, shorter, shorter. So I will write this negative, meaning it's getting shorter and shorter, the length. Okay. But if you want positive, that's also fine. Because if it's positive, the other will be positive, the answer will be positive. But if negative, because if this is also shorter, this should be negative. The answer should be negative, meaning it's getting shorter. Okay. So I think don't worry too much about the signs. Okay, as long as you understand the logic and you make consistent in your all questions, the number should be the same. The number should be the same. And I will make dB and dt is also -60. Um, and I will write this to a or at a 0.3, b 0.4. I will write this to 0.3. A is -50 plus 2, 0.4. This is -60. And at 0.3, 0.4, C is 0.5, right? With category. So 2, 0.5, and then DC, dt. Okay. So it's -30. This is 24, 48, right? And this is half, so it's just canceling. So DC dt is -78 miles per hour. Notice that if you just making positive, it will be positive, but the same number, right? So meaning it's 78 miles per hour. But don't worry about this negative part, okay? This is just means that the C will be shorter as it's getting closer to the intersection. Okay. But if you want to write this as in the positive, it's also okay. It's also okay. Have you practiced with TA, the related rates, or not yet? Last Friday, not yet? Okay. Maybe this Friday we will be practicing the related rates. Okay, any questions? Any questions first? Any questions? So this is actually not really using any analysis from uh, specific calculus. Okay, this is basically how you read the questions, how you understand the questions, and how you relate the questions with some formula that you can find. Usually the formula is quite simple. It can be area, triangle, circle, Pythagorean. That's the most formula that are used in related rates. So we will be using a simple formula, and then you will relate all the informations, and then derive the formula and plug in the information and look for the one you are looking for in the formula. Okay. Okay. My suggestion is try to read several questions from the textbook. Okay, from the chapter related rates. Okay. Read and try to maybe understand the questions first. Okay. because the answer for all the problems should be like in short and simple in related rates, unless the question is long. Okay? Unless the question is long, but usually the answer is simple and short. And if you understand the questions, several questions from the textbook, I think that should be fine. Okay, that should be fine. But related rates. Okay, now I will move a little bit. Okay. Um, this is yesterday. Okay, I will move to short sections about the growth rates. Okay. Okay. Let me write the growth rates. Or in this case, how log are used, or how exponent and log are used. Okay. So remember that if you have x squared, x cubed, and so on, and you have 2 with the power of x, 3, 4, maybe 10, and also you have the x to the x, maybe x factorial. Okay. Okay. If your x is, let's say, 1,000. Okay. Your x is 1,000. This is 10, 1,000. This is 1,000,000, and this is keep increasing. This is 12, right? But what will happen here? This is 2 with 10, 3. Or this is 2,000. And this is 3 also 1,000, 4, and so on, right? And this part is 1,000, 1,000. It's getting crazy, right? So what I show you is if you have this, the first one is polynomial, linear growth, meaning the growth is based on uh, the power index. Okay? And this is what we call the exponential. And then this is what we call the factorial. So from the top to bottom, it's getting faster. Faster. If you see the graph, you will see that the exponential will be above the polynomial. Okay? And also factorial will be even faster. Okay, so if you have this crazy number here, okay, the easiest way to write or to observe or to analyze is by let me write here. Like for example, I have a 10, 3, 10, 6, 10, 9. Let me write the 2 with 1,000 as maybe around this 10 to 300. I will make all in the base of 10 approximately. Okay. Maybe 10, 10,000. And so on. Okay. So if we take log, okay, if you take log, this is just 3, 6, 9, and so on. Okay. So if I draw the log, okay, let me have this is 1. 1 meaning the 10 with the 0 power, okay, and then 10, 100, 1000. So I can write this 10. Also, I can move backwards. This is 1 over 10, 1 over 100, and 1 over 1000. This is the minus 1. This is minus 2. This is minus 3. So I also can make this in, so this is log, this is log. Okay. So I can also write this just 0. This is 1. This is 2. This is 3. Okay. And how about 0? 0 in this log. Okay. We cannot write 0, right? There is no, right? Okay. So we cannot write it because it's in log. Okay. But besides, okay, if we are using the log scale, for example, in I think in physics or in chemistry, you will do. I think chemistry, right? In log, usually in pH, right? pH. Okay. So in a practical way, okay, if you find any relations, maybe populations or maybe like chemistry, you find the relations with the let's say a, and you have the variable x and with power of n. Okay, you have these models. Okay, of a is constant that you need to define. Remember, this is a constant, and maybe from the plotting, okay, from the plotting the graph, or maybe if you get the information that n maybe is 3 over 2, maybe we can draw. Uh, we can draw. Maybe the graph will look like this. But when you draw 3 over 2, usually if you draw like in the paper, not using any calculator graphing or any websites, it will be difficult to differentiate, okay, if n is 3 over 2 or n is 2. The quadratic and 3 over 2 in the power, it will be difficult to differentiate if you draw just using your pencil and paper. It will be difficult. So the way to solve this problem, how you observe any power index, is using log. Okay, if you're using log, okay, let me move to another page. Okay, if you're using log, so using log, let me write the. So let me use log and log. Let me solve this first. Okay, so log a plus log x to the n, and I will make this n just moving here. Okay, so basically we can have if this is log x and this is log y. Okay, practically we're just having linear. Okay, which is more easier to find. Okay, if you want to make or to find this linear functions, and finding so the n will be the gradient, right? And you can practically get a from the c here. Okay, and it will be much more easier. Okay, and also if you think also it can be also used like this. Okay, so this is maybe this is the log is in y, and maybe the x is just x. It can be also observed like this. It depends on your formula here. Okay. But what the important here is the with log you can solve some particular problem in if you have any models in power. Okay, so this is just mathematical models. So what I want to bring here is if you have exponential growth and decay. Okay, uh, let me write in the new slides. Okay. So if you have exponential growth and decay, you can solve some problems here using log. Okay, but let me go into the exponential first. Okay, so it can be used mostly in populations. Okay, to determine the populations, and you know, uh, if you go for statistics, you will learn how to predict like 20, 30 years from now how much population will be like in Taiwan or maybe in the world or maybe it's in some country and how the growth rate will be. Okay? So it's populations, and the other is the radioactive decay. Anyone knew about the radioactive? What does it mean? It has a radiation, of course, yes. But what is the consequence by having radiations? Okay. Hmm? Yes, decomposed particles and itself. Okay. So if this block of let's say this is radioactive material. Okay. So it will be having radiations, okay, to the surroundings, but the material itself, over the time, it will getting smaller. The radioactive material itself, okay, that's what we call a decay process. So this is decay. So over the time, it's getting smaller. Okay. Okay. So the growth or decay, let me write some notes here. So rate of change is proportional to the quantity. So rate of change is, we learn is as in calculus is derivative, okay? Or dy dt, or any symbols y prime, etc. And the quantity is the our functions. Okay. We can write this as a is yeah, it's meaning this is proportional. So A is proportional to B. And we can write this, maybe in physics or in chemistry, you always see this proportion. A is KB. So having some K. So K is a constant. It can be a fraction, it can be some number, okay? Constant of proportionates. Yeah, it's a constant. So what does it mean rate of change is proportional to the quantity? So if you have, maybe I've told you before, like many, like for example, rabbits or cats or dogs, if the population itself is larger, how they grow, okay, how they will breed and having children is also larger. Okay, it's proportionate. Okay, so if they are growing larger, if they can multiply by themselves, okay, what is let me have this. So if my functions, okay, is some k of my derivative, okay, or I will write y is k y prime, okay. What functions that can be uh, perfectly fit with those relations? So you need to have some functions. When it derives, it will be that functions. So you have y, k, y prime. So if you have y and you derive that y, and it will be back to itself. Okay. So remember the functions. So if you have e to the x, this is still e to the x, right? So why this e is really suitable for explaining exponentiations, because when e derive, it becomes itself. So if you imagine the animal, it will be multiplied by itself, right? It will be breeding by itself, right? So we can use this to make our functions looks like e with some, let's say I will change the x to kt. So when we derive this, it will be ka e kt, and uh, this will be another constant k. You can, because k and a is constant, we can just combine those constants together. So it proves that y and y prime is having a relations there. So we can simplify this, become y just k y. Okay, and given the a k, it's the real number. Okay. Okay. Let me write some number, some info. So y is the value of a quantity y at time t, and it's proportional. So this is proportional to y. Okay. And k is, if k is greater than 0 and k is less than 0, this is natural growth, and this is natural decay. Okay, let me give you just one example. Okay, and if we have time, we can go back here because it's a short section. Okay, let me give you this example. So let me give you. It's a petri dish. Okay. Um, the red color meaning the cells. Okay. Yeah, I hope you can see that. Let me write this 5,000 cells, and the time is 30 minutes. And and the cells is getting increasing in number. Let's say this is becoming 20,000 in just 30 minutes. Okay, so find population at function. So you need to find the functions. So 2, when will it be 100,000? And then rate of change after 1 hour, and uh, when it has 50,000. Okay. Okay. So I think all the assumption for population growth in this section is based on natural growth. Okay. So you just need to write this dp over dt is kp. Okay. And your p is, you can just write based on your exponent e and then kt. Okay. And all the k is greater than 0. K is a, k is the element of real number. We say that the 5,000 is our initial populations. We can write the initial populations is a. So we can just having a is 5,000. So the total functions will be p is equal 5,000 e 80. Okay. So this is the functions. So when it's getting 20,000, 20,000 equal 5,000 e k. Let's just make 30 minutes here. Um, it's 4 e 30k. Okay, so ln 4 is 30k, and we can get k is ln 4 divided by 30. Let me just finish this first. So number 1, the function will be 5,000 e ln 4 30t, and number 2, when it has 100,000, it's become 20 e ln 4 30t. So um, and t become 30. Yeah, you can calculate this, maybe around 64 minutes. And rate is dp dt. We just differentiate dp dt and then ln 4 and t is 60, right? 60. So it will be 500 over 3 ln for e become 2 ln 4. It's become 503 ln 4, 16. We will have some number here, and the number, the other number, the rate when dp dt is, and you need just to multiply with 50,000, and it will be some number here. Okay. Okay, I think do you get this also, this calculation also in physics, or do you get in physics this populations growth, cells, bacteria, radioactive decay? Do you get it in physics or no? Not yet. Okay. Okay. So basically, okay, the idea is you are having the, so this is the basic. Okay, uh, P is equal A, and you multiply with E, and it's having the power of K and T. This is the constant that you need to find at the very beginning to define your original functions of the populations. Okay? And T is depends on the time the function is working on. Okay, is it 30 minutes, 60 minutes, etc. So usually it has some information, and you plug in the information, you get the original functions, and from that original functions, you can basically input the other questions. Like example, they were asking when the cells or bacteria is at some number. You just plug in the number and getting another number, okay, out there. Maybe it's asking the t, maybe it's asking the number. It can be both. Okay, it depends on the question, but uh, this is basically your original function. And when you are asking the rate, you just derive the p, become dp over dt, and derive the e. E you can derive, so this k can be come up front, and it's still here. Okay, and this will be a new constant, and you can practically calculate the rate of change. Okay, so it can be any like it can be growing, or maybe it can be decaying. For decaying process, decay will be minus. Okay? Decay will be in negative. This is k greater than 0. Okay, but it will be like really short sections in your calculus. But please remember here, I'm not sure whether this will be in differentials in your engineering of math, because in engineering of math, first you will solve all the linear equations in differential growth. Okay, so also in, I think you will I'm certainly sure you will learn in chemical engineering, I think, and also mechanical, yeah, this form. Okay. Okay. Okay, meaning this dot here, yeah, you can just calculate. Okay, you can approximate with some number there. Okay, now back to the big picture of calculus. Okay, so this is just a small section how you are using the e and the in the exponential growth and decay. Not really in the exam. Okay, it's just additional. Okay, let me go to the next section. I think this will be the last the last sections in this chapter, and we will finish the chapter 3, and we are going to move on to chapter 4. So it's called the linear approximations. Okay, let me write at x equal a. Okay, a is any number, any constant. Okay, um, I can write the dy over dx or dfx of over dx is f prime of a by limit definitions. I hope you still remember this. Okay, by limit, we know that uh, this is our approach. Okay, if I remove the limit tools here, can it be true? Is it true or not? If I'm removing this limit, is it true or not? Can we say that the f prime is actually just fx minus fa divided by the distance? No, right? But if I say if a is close to x, and I will remove this, I can't, right? Okay. So let me write this. Let me write this in approximations. Okay. So because the sections is called the approximation. So this is fx minus fa over the x minus a. Okay. Let's just solve it this terms, and then I will show you what this looks like in the graphs. So if I solve it, um, and I have the linear functions, which is the fx. So I'll move to the right side. Uh, okay. It seems I get the the linear terms for whole this the f prime. Okay, so I get this expression. Okay, but how we can use this approximations really? Let me draw you some graphs. And what does it mean really? If I have the curve, the blue one, okay, uh, let me write this as f of x. Okay, let me make some point here. This is a, okay, and this is a f of a, okay, and then making tangent line at that point. Okay, so what this expressions, the linear expressions means is actually our tangent line. Okay, okay. So tangent at x equal a is actually our f prime of a. Okay, and from here also we can make our own expressions, and we will get similar approach. Okay? This is f prime of a, and x. Remember how to find the equation of tangent line. Okay, this is very similar to that, but I will write the y is y1 is our fa, and I will write fa plus f prime a x minus a. Okay, so the tangent line will be the same as the functions, the curve. Let me see here. Okay, you see the curve is having a curve, right, going above. But when it's nearby this point, it seems the same, right? And that's when we can use our linear approximation. When we can approximate this point with nearby any x that has having a closer to that point, we can use just our tangent line. Because if we see graphically, it has the same shape. Okay? But if you are moving too far, like maybe here, it has a gap, right? So it will be different answer. Okay? But when you are getting closer and closer, you will get to almost exact answer. And how we are actually using this, okay? Let me show you how we are dealing with this, the graph, okay? Okay, the question is find square root of 9.06, okay? Using calculus, not calculator, okay? Using calculus. So we need to find the square root of 9.06 using calculus. So how do you do? How do we solve this? Okay, first you need to define the number first. It has a square root, okay, square root of some number. Okay, let's just say the original function is square root of x, the variable x. Okay? Let's just write this functions is square root of x. Okay, and let me just derive this functions, and it will be 1 over 2 square root of x. Okay, and then what we can do is, from previous expression, we have a, right? We have a, okay? And you see square root of 9.06. What is the nearest number that we can square root easily? 9, right? If we square root 9, we will get 3. So let's choose a to be 9. Okay. So choose a to be 9. Why I'm choosing 9? Because if we square root 9, it will be easily getting 3. Okay. So I will write a pick a close to our questions. Okay. So the FA and then the F prime A will be, okay. So my whole functions, or I'm using the approximations, is 3 plus 0.006. Okay. So this expressions is just the formula that I derived before. So this is the fx. This is fa. We choose fa. This is plus. This is the x minus a. And this is the tangent. This is x minus a. Okay. X minus a is from the 9.06 minus 9. The difference is 0.06 x minus a. And then this is the gradient or the tangent. Okay. But you can see from these expressions, the more x minus a, the more smaller this is, I think it will getting to the real exact solutions. Okay. If we multiply 3.01, 3.01, it will be similar to 906, but I think it has 01, 90601. If we multiply this with another 3.01. Okay. So we can approximately say that so what really happened here? Okay. Let's say this is the square root of x. Let's say this is 9. This is 3. It's bad, right? But let me just write 9 and 3, and this is the square root of x. Okay. And 0.06 from 9, I will write maybe here. This is 906, and it will have the. And actually, what we are looking for is here, the tangent here. So in that point, the tangent is really close in shape with the curve. Okay. This is what we call the linear approximation. So whenever you have um, problems that want to be solved by approximating some number of value, you can use this linear approximation. Another another idea from this linear is actually a method called the Newton's method. It's actually will be I will deal that later in chapter 4, but let me introduce you in this class, okay, the Newton's method, because it's actually the same principle as the linear approximations. Okay. So this is an example. So let me write, okay. Um, before is the square root of x, right? When x is 9.06, right? The previous question. Let me write a new function, okay? Inverse of this, okay? Inverse of the square root. What's the inverse of the square root of x? The inverse. Anyone know? What's the inverse of if the fx is square root of x? What is the f inverse? What? Anyone know? Inverse? Hmm? Log? No, no. Yeah, x squared. X squared. This is x squared. Let me write a new functions. F with the big F x. Okay. Let me write this is x squared minus 9. The same using the same idea from the linear approximation. So x squared minus 9.06. Okay. Uh, before we are using a is 3, right? So let me write a is 3. Okay. And from here, I will write fa when a is 3. So plug in a, so 9. So 9 minus 9.06, it will be negative 0.06. Okay. And f prime a is just 2x, right? 2a. So it will be 2, 3, 6. Okay. Okay. So uh, I can write here x approximately 3 minus, okay, minus 0.06 over 6. Okay, I can rewrite this. Okay, so from the original one, let me write here. So the original one is fx. So I'm moving the yeah, just like that. Okay. So So this is maybe 3, and then we're dealing here, and we are making the tangent here. Not good. Okay, so this is 3, 3 and 9, right? And this is another, let's say, x. Okay. So from these calculations, I get 3 plus 0.01. It's 301. Okay. Do you get the idea? Okay. So when you are dealing with the, let me go here. Okay. When you are dealing with the linear approximations, you get actually the fx, right? The fx, for example, in this case, the fx is the 906, and square root is 3.01. Okay. And you get the tangent line, okay? The equation of tangent line, this whole equation, okay? But in another way, when your fx is equal 0, okay? So when your fx is equal 0, meaning you can find the real roots, right? So from this one, okay, this is it's actually called the Newton's method. It's reversely finding the one that crossing the x-axis, so finding the roots here. But it's you see, it still has like this small gap. But I think because I draw it not really good, it should be like closer. Okay. But even though you are having like a gap here, we can do another one. So we have, if this is the, let me write, this is x0 and this is x1. Okay, we can find x2. So let me draw another one here. So I'm getting point here, and let me draw the tangent line and crossing the x-axis. Okay, and here is the x2. This is getting closer, right? So we can estimate, okay, finding the real roots using approximation, using the Newton's method. So we can have 1, 2, 3, 4. If you choose correct x0, maybe you have only 1 or 2 iterations. But when your x0 is not really good, maybe you have like 4, 5, maybe 6, 7, like x7, x8. That's possible. So you can have more and more closer to the real roots of the curve. Okay, the real root is the blue one here, right? Okay, so Newton's method, you can use that to getting closer and closer to find the real roots. Okay. Or let me write, maybe to make it clearer, more clear. Let me write from so x minus a is, so this is when the fx is 0. So meaning fx0, meaning you can find the x-intercept or real roots. Okay, I'm moving the Newton's method to this chapter just to show you that actually we are dealing with the same expression here. Okay, this is the linear approximations. But you can rewrite this, and when your fx is 0, it meaning it is crossing this x-axis, right? When fx is 0 is here. So when fx is 0, you can find your your roots. Okay? So I can rewrite these expressions, okay, and moving this to this part, okay, and I can find this x, okay. So I'm moving the a here, okay. So, for example, if this is the x0, x1, okay, and a is our x0, it's minus the f prime a, okay, and then the same thing you can do x2, and this is x1 minus this should be the let me use the same variable. And then you can have more and more, like x3, x4, x5, like getting closer, 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 and you are cutting the x. Okay? And that is the it's called the Newton's method. Okay, it's called the Newton's method. Okay, so here you get the 3.01. Okay, um, let me go to, like, if we use this 3.01, like if we are using the 3.01 in our calculations, so f should be 0.0, and then f prime, this should be 602. Okay, so from this itself, okay, it's already 0.0001. Okay, and at the beginning it's already 0.06. So when you're getting closer, your actually the distance is error. Okay, your error. So this distance is the error. So distance or gap is the error. Okay. So how many percentage you are from the real roots here, the exact number here. Okay. And whenever you have any like for example, you start from here, get x1 here, and you say, oh, it's still big error for me. Let's just make a new one and get closer here. Maybe if you think that this is also big for the error, you can make a new one and make going up here, and it's getting closer, right? And getting closer, 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 and closer. Okay. And your error, your distance here, is will be getting the 0.00000. And sometimes from here until the second one, this can be quadratic. This can be like you just squared and then maybe cube, and it will be like it has a many number 0 here. Okay, so that's Newton's method, which is actually really really good for finding the roots. Okay. And do you have any idea? This is just a simple curve, right? Can you think when this method, finding the roots, can be fail? Can you think? What do you think? So, because it's just a simple curve, okay, we can put like x0 anywhere, maybe here, getting here, and from here, maybe going up here, and then getting here, and then getting closer, 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 closer to our real roots. But this Newton's method actually, it's really powerful, but it can be failed. It can be failed. Okay? For example, if you have uh, like a like this curve, you can have like from x0 and you get x1, and from x1 you're going back to x0 and cycles. Okay, it's the Newton's method failed. Okay, uh, let me back the to um, let me back to the real roots and the linear approximations. Okay, let me back to here. Okay, any questions from linear approximations? Any question from here? Any questions? Okay. Wait. Okay, maybe I will give um, some example, okay, before we are going move forward. Okay. Or maybe different functions. Let me check different functions. Maybe just using this first. Okay. So can you try? And also try estimate the the first one is just square root of 17. The same cases with before, just square root. Okay, so the function is square root of x, and the other one is the 1.998 with the power of 4. Okay, and then estimate both of these cases using calculus. Okay, so meaning do not use any calculator. Try to solve this one. Yeah, this one. Okay, some mistakes that might happen when you calculate the linear approximation is the plus minus. Okay, so sometimes if, like for example, it's 17, maybe the easy one is 16, right? So it's less one than the 16. Oh, it's more one than 16. But this one, the easiest number is 2, right? 2 is greater than this one. So maybe x minus a, you need to flip and make sure the positive and negative signs. Sometimes mistake that happen is you are mistaken the positive and negative signs. Okay, to approximate the um, 17, and to approximate this from the 16, right? Plus the 17 and 16 is just 1. And we need to find the, so it's just 4 plus, okay, can directly plug in. So what does it mean is any estimations you make, okay, any calculations, meaning it's the one you are choosing, the easy number that you can predict that will be easy, plus the distance, meaning the distance is the unknown number with the your a is 16. The distance is just 1, right? 17 minus 16 is just 1. Okay. You need to multiply this with the derivative. If your function is just square root of x, so the derivative is 1 over 2, and then plug in the number you are choosing. Okay, it's 16. Okay, I'm writing it's multiplied by 1, or 17 minus 16. Okay, okay. So the idea is uh, the number that you choose, that easy to calculate, plus the distance between the number that you choose with the questions, and multiply with the derivative, and you plug in your number. That's easy to calculate. Okay. And in number 2, the distance will be negative. Okay, the distance will be negative. So here, maybe write choosing A is 60. So I will write like directly just, and I didn't write the expressions clearly, but uh, I'm writing the answer, the plus, and then uh, it should be, and then multiply with the 4. This become negative 0.0002. So your 16 minus 0.00, no, 64. This 32, and this should be, okay. Maybe this around 15, right? Okay, got it? Understand? Understand? Okay. You can write like with the whole functions, the fx is like x to the fourth, and the first one is square root of x, and write all the necessary derivatives. That's fine. And if you just go directly like this is also just fine. Meaning you are understand that this is actually your fx, fa. This is x minus a. This is the derivative, and you're plug in the number a here. Okay. Okay. Any questions? Any questions? Okay. I think it's in practical, it's easy to use, right? Okay. I think I will just stop here. Okay. So oh, by the way, if the question is asking the linearizations, okay, this is just the name, okay. So this is called the linearization. Sometimes you are writing Lx and it's equal that point, okay. This is just the terms, okay. This is also called linearization, meaning you have curve, you want to approximate the curve with a tangent line, you call it linearization. Uh, you can write this fx with Lx. It's meaning the linearization, and basically it's just the same thing. Okay, just the same thing. Just a name. It's called the linearization. Okay? So if you find in any textbook the linearizations, its meaning is doing this linear approximation. That's the same meaning. Okay. Okay. If there's no questions, so uh, we will stop here and we will see you next Friday. I will go to a new chapter. So I will upload all chapter 1, chapter 2, chapter 3, all notes to Moodle system. Okay.